Good morning, I'm Vivian from the University of Hong Kong. Today, I'd like to talk about chemistry as central science to energy, materials, and biomedical research. I hope I will be able to convince you that chemistry will be able to contribute towards multidisciplinary areas of research. So if you look at the world energy consumption, the annual global energy demand is around 13 terawatts. And around 80% of this is coming from burning of fossil fuels. And by the year 2050, we need something like 27 to 33 terawatts. And so by that year, we need an additional 14 terawatts on top of what we need today. So it's really huge. So how are we going to cope with that? Particularly when we have growing population, rapid economic growth, as well as high demand for a modern way of living. Now, obviously, the fossil fuels won't be unlimited, right? We have upcoming depletion of these. Of course, there are people arguing that we still have many years of oil, natural gases, coal, and also in the deep sea, we have methane cathodes. But even if we have plentiful of these, we cannot keep on burning it, right? Because it will create or generate a lot of carbon dioxide. And this creates a problem of global warming and climate changes. So there's an urgent need for us to have a carbon neutral or low carbon economy. Now, what are the ways to solve this? There are many ways. And one way is if we can develop clean sources of renewable energy. And obviously, there are many ways to give you clean sources of renewable energy. We believe solar is really a very attractive option because 1.5 hours of sunlight falling on Earth globally, we already will be able to get 13 terawatts a year. And actually, this is a little bit cheating because not every piece of land is lined up with solar panel, but still they are huge as compared to other sources of renewable energy. Another one is, why don't we cut down on our demand, right? So for example, if we replace all the solid state lighting with more energy efficient lighting, then probably we'll be able to save some energy. Now, but before I go into details, I want to sort of remind you on what is light, right? Light is actually electromagnetic wave. And the light that we see, so-called visible light, is only a small portion of it. And here, the color we see actually is the color that's complementary to those that are being absorbed. For example, if blue light is being absorbed, what we see is the remaining part that gives us the yellow solution. Or if green light is being absorbed, so green light is being absorbed, so very little can pass through, then what we perceive it is a red, sort of red-purple color solution. So it's those colors that's complementary to those that are being absorbed. But for emission, if the emission of light, the energy gap matches blue frequency light, what we see is that we see a blue emission. Okay, so don't mix up the two. They are different. Now, so when we have a molecule, we shine light, it goes from a ground state to generate the excited state. And this excited state having excess energy will try to get rid of the excess energy. And it can do so by non-radiative decay, like vibration, sort of rotation, collision, and so on. And this is something we don't want. But if it goes back to ground state with release of light, it's called radiative decay. We get luminescence, okay? Or if we generate charge separation, then this charge separated state, we can make use of a hole and electron to do useful work. Or we can also do other photochemical reactions. And we are very much inspired by nature photosynthesis, where you generate a long-lived charge separated state, and you can use the electron hole to do useful work, okay? Now, here, as we mentioned, we want to really control the excited state so that we can make use of the light to shine onto ground state to generate excited state. And if we understand the excited state, we can convert the light energy to some useful work. And here I will elaborate more. Here, if you have a long-lived charge separated state, you have an electron hole, and if you can collect it at the two electrodes, then you'll be able to generate solar cells. And this is how the solar cell works. Or alternatively, you can make use of it to do oxidation of water to oxygen, oxidation of methane to methanol, for example, reduction of water to hydrogen gas. And we want to maximize the absorption of light from the sun. So this is the solar spectrum if we can harvest sunlight, right? And Obviously, as I mentioned, when you generate excited state, they can also go back to ground state with release of light. So you end up with luminescent material, and here you can use it for imaging, for bioimaging, labeling cells, cancer cells. You can also, if you have the three primary colors, the red, the green, the blue, you'll be able to make full color display or white light for lighting, or you mix yellow and blue, you can also end up with white light. And you can also make use of light to do photochromic reactions. So this is photochromic materials. You shine light, you convert the color from one to the other. So it's light-induced color changes. So you can cut down on the light into a car or into a room. So to cut down the power that is needed to achieve a certain temperature. So again, energy saving. You can also use it for data storage as well, because colorless you can consider with 0, the color one to be 1, 0, 1 will be binary data storage. So I will elaborate more on that. So we're very much interested in molecular functional materials because they are, we have a lot of different synthetic methods. There's a versatility there. They are easily processable. We can understand the structural property relationship so that we'll be able to achieve function by design. And when we talk about materials, it's not a single molecule we are seeing. It's a whole ensemble of molecules packed together. So if we have a way to manipulate the intermolecular forces that hold them together, then we can affect the molecular packing, the orientation, the alignment, and so on. And probably we can come up with some innovative molecular materials. So we work on this class of platinum compound. I don't want to bother with details. It's a flat molecule. Just by changing the ligands here, we'll be able to change the absorption color. We're able to change the emission color. And one of them I show you here when RSH is an orange color emission. And we can tether it onto a receptor, a cavity that can selectively and specifically bind potassium ion. And when it binds potassium ion, it will turn on the emission, orange emission. But other metal ions won't be able to do it. So you can do it for selective sensing of potassium ion, and even for imaging potassium ions in a cell for mapping. Now, but because these are flat molecules, they can actually come together to stack on top of each other to turn on something called a metal-metal interaction. And this is really interesting. It has bond strength quite similar to that of hydrogen bond. So this molecule actually will be able to crystallize into a dark green crystal and a red crystal form. It's essentially the same compound. Exactly the same compound, just the way they pack differently. This pack linearly, it is dark green in color. This pack in a discrete dimers arranged in zigzag fashion is red color. And if you dissolve either of these in solution, you end up with a yellow color solution because they are well dispersed. They exist individually and well solvated. But when you add a bad solvent to it, you force them to come close to each other because you reduce the solvation. And now you turn on the metal-metal interaction, you see the blue color change or sometimes magenta color change. And instead of the orange emission from a yellow color solution, you now have a near-infrared emission coming from this blue or magenta color solution. And besides that, you can use temperature to modulate this. When you reduce the temperature, again, you are reducing the solvation, forcing the molecules to come close to each other. Again, turn on the metal-metal interaction. They give you this blue color change as well as near-infrared emission. So they are so-called thermochromic, temperature-induced color change. So you can use it to sense temperature. Or you can also make use of our metal compound. We make a thin film under humid air. It's yellow color, orange emission, because they exist individually. But then when you expose it to alcohol vapor, they come close to each other. Again, they turn magenta color, purple color, near-infrared emission. And then when you expose to vacuum, they come even closer. It's further to the sort of deep violet blue. And then, so you can use it for sensing alcohol. Here I have a short video clip. So you have the yellow thin film. You dip it close to alcohol, not touching alcohol, but exposed to vapor. This is in real time. You immediately see the purple color change. And when you retract it, it fades. It gives you back the yellow color. You can also see the orange emission coming from yellow thin film. And when you dip it close to the alcohol, you see the alcohol vapor will convert to deep red to near-infrared emission, but our eyes are not so sensitive to it. And when you retract, it will go back to orange emission. So you can detect whether people have been drunk or have to take too much alcohol right? With a breath analyzer, just by noting the color and emission color changes. Now, our compound also is positively charged. They can also be electrostatically attracted onto some polyanion, a polymer. And then you bring them close to each other, again, turn on this metal-metal interaction, give you a magenta color as well as near-infrared emission. And with that, we can now make use of it to design many sensors, many sensing applications, sensing DNA, sensing enzyme activity, pH for imaging, and also following amyloid fibrillation for dementia, and also sensing RNA, and use it for imaging nucleolus. So here, this is an example where the nucleolus will be turned on with near-infrared light, red light, and you can do it for imaging nucleolus. And you can also use it for screening RNA synthesis inhibitor, because it will give you different sort of imaging of the nucleolus and so on, and you can use it for screening inhibitor or even screening some drugs. Now, I've also make use of it to make materials. We have already seen this color change, and we can also change the morphology, change the colors. We can also make hetero junctions and so on, nanotubes, which I will show you, and 2D materials I'll show you later on. So this is a molecule. When it dissolves in water, it's sort of magenta color, forming spherical vesicle. But if you have increasing amount of acetone, then it goes from magenta to orange to yellow to green to blue. And the blue species actually are rod-shaped structure because they have very strong metal-metal interaction that directs it. And so you can imagine that just by changing the packing, you can change the morphology as well as the optical properties. And here, another one, we tether two of these molecules with a rigid spacer where the two metal centers are far apart. It's yellow color solution, orange emission. But when you insert a gas molecule there, you have 3 platinum in a row. Now you turn on the metal-metal reaction to give you this red color change, where here you have 2 pockets, you insert 2 gas molecule there. Again, you would now put platinum 5 in a row. This time, instead of red color, it goes further red shifted to a green color because of stronger metal-metal interaction. And here you have the one with 2 pockets, one with 1 pocket. When you mix them together, these are their colors. You get a deep blue color because you're again putting 5 platinum in a row, but they are intercalating into each other, a very tight metal-metal interaction that give you this further red shift to give you a blue color. So we have now a way to put molecules in an orderly fashion as we wish, and giving them very different optical properties and also sometimes very different morphological properties. Now, this one is another one. With this molecule, we can make nanotubes, very monodispersed, lamella packing, whereas you just introduce 3 bulky groups here. They are essentially identical, just 3 bulky groups here. Then instead of getting the tube, you get the ribbons. And you see, besides the morphology differ, the color, the optical properties also differ. So we can understand all the mechanism. We can also make a tri-platinum species with 3 platinum square plane flaps lying sort of orthogonal to the central ring here. And then they can dimerize. And when they dimerize, like a Y shape, when they dimerize, you can imagine they get a honeycomb porous structure. And we can see from AFM, they form layer structure, monolayer, bilayer, trilayer, and they are porous with pore size around 3.6 to 4 nanometer. And as I've said, they come in layers, very orderly fashion. And if we make a membrane out of this, we can actually use it to extract heavy metal waste, platinum waste. And then later on, we can recover the platinum waste out of it. So this is very important for cleaning the environment. And also, if we make a thicker membrane out of these molecules, what you see is that because the pore size, as I said, is around 3.6, 3.8 nanometer, so we have a mixture of red emissive and green emissive quantum dots, and only the green emissive quantum dots that are smaller than the pore size can pass through. The one that's larger will be retained up there. So you can use it for nanoparticle separation. Now, besides that, we can also do a co-assembly with our molecule. We grow a certain length. We use another unimer, it grow another certain name, is like growing heterojunction. And we can also make use of the metal-metal interaction, as I've said, with bond strength similar to a hydrogen bond to line up gold nanorods either in an end-to-end assembly or side-by-side assembly. So we can really manipulate intermolecular forces to make them put in a certain order. Now here I want to switch gear a little bit because as I mentioned, we make these molecules that absorb light. They can harvest sunlight to do photocatalysis, to make solar cells, or to do sensing, as I've shown you. So we need to have a control of their assembly, their packing, their orientation, and so on. And also the color of their absorption, the color of their emission. But besides that, some of them, as I said, when you generate excited state, it will come back with emission of light. Now, if we can replace lighting with this organic light emitting diodes, OLEDs, it's more energy efficient because for incandescent light, more than 90-something% of energy is really lost as heat. And actually, globally, we need something like 20% of the energy just for lighting. So if we can replace it with more energy efficient lighting, that will be great. So you can also imagine that with OLED, besides for lighting, you can also use it for thin film, bendable, flexible, stretchable. So you have all these bendable curved TVs, monitors, smartphones, VR, AR, right? And even lighting in cars and so on. And here is really the timeline of products. The first one is the Kodak camera. And now you have all these smartphones, rollable, bendable, iPhones, smartphones, monitors, display, VR, AR. I don't want to sort of elaborate more. Now, and as I've already mentioned, when you shine light, you generate excited state, they will dissipate the energy either as heat or as light. So this is photoluminescence. But actually, electroluminescence, which is the principle of OLED, works a little bit differently. Here, we inject an electron in a hole, and when they recombine, they form an exciton that emits light. Actually, it's just a reverse principle of solar cell, because for solar cell, you shine light, there's a charge separation, electron hole, you collect at 2 different electrodes. That's how a solar cell works. And now you inject electron hole, and when they recombine, they generate exciton that give off light emission, okay? And actually, there are different generations of OLED, different mechanism. I don't want to bother with detail, but we also contributed a new mechanism called TSDP that will be able to make robust blue emitters. And actually, we work on a very interesting class of gold emitters that we were able to make them the first in the world to be room temperature phosphorescent. And now we have many types of gold compounds. And we were able to now make different colors and with very long device lifetime, very robust. One of them with LT50, that means when the luminance dropped by 50%, it takes 470,000 hours. And 1 year is only 8,760 hours. And so all these are with accelerated tests. And we also introduced the TSDP, which I've mentioned. They are highly robust. And now we have all the different colors, red, green, blue, yellow, and so on and so forth. And another way is, why should we be able to control the molecular packing, molecular orientation, and so on? Because these devices are multi-layer devices, and each layer could have different refractive index. And so not all the light emission would be able to be extracted out. And only those molecules that are lying horizontal with the transition dipole moment vector that is horizontally aligned will be able to come out more easily. So we can increase the outcoupling efficiency if we can control the molecules to lie flat. And so that's why we need to manipulate the intermolecular forces. And what's the future? You can imagine transparent OLED display on sliding door. You have the entire wall, entire window. You have transparent smartphones. You have foldable, stretchable ones. You have it on textile. You have 3-dimensional sort of display. And actually, besides, they can work as OLEDs. They can also act as organic resistive memory, where you apply a voltage bias. What happens is that it turns to be high conductance from its original low conductance. So if you call the low conductance 0, the high conductance 1, you have the 0, 1, 1, 0, 0, 1 binary code. You can use it for binary memory. But we can also design molecules that can have ternary memory, low, medium, and high conductance. Now, instead of a storage capacity of 2 to the power n here, you have a storage capacity of 3 to the power n. So you really improve on the storage capacity of this data storage system. And besides that, we can also use light as you shine a certain wavelength of light, it turns its color, it stays there for a year. And then when you shine another wavelength of light, it returns back. Again, you can consider it to be 0, this to be 1. So you can have optical data storage, and then you can read it as well. So one is like a writing, the other is an erasure process, and you have the reading process as well. And here I show you one example of a molecule that we make. We coat it onto a quartz plate. We shine UV light. This is in real time. They immediately change the color to sort of brownish red tint. And then they will stay there for a year without change. So this is like a writing process. And then when we shine visible light, white light is visible light. And again, in real time, it will return back to the original state. So it's a 0, 1, 1, 0 writing erasure process, and we can read it for reading as an optical sort of readout. And so with that, I really want to close. So this is Hong Kong by night, or you are welcome to come to Hong Kong. And I just want to share with you my journey. I was trained as a coordination chemist, inorganic chemist. I tried to learn organometallic chemistry. And then after I learned this, I make luminescent materials. I make molecules that could absorb sunlight, that could be used for making solar cells, for photocatalysis, and those that will generate excited state to give off emission. I also learn about how to make organic light emitting diodes, to make OLED devices for display, for lighting. And I also use the luminescent materials for sensing, for bioimaging, for example, imaging cancer cells, for screening inhibitors, for biomedical research. So you can imagine that one should not be narrowly focused. You should be open-minded. You should learn things that you have never learned before by yourself. So that's why a very sound foundation of science, the concepts and the principles need to be really clear. Then you can really learn by yourself. It's a lifelong self-learning process to upgrade yourself, so to catch up with all the very fast-growing science and technology development. Every day there's new stuff coming out. And how can you learn all these, right? You learn by yourself. That's why you need to have a very solid foundation in science. So with that, thank you very much.